So the first one is the enhanced mobile broadband. So the improvement of the peak average cell edge data rate capacity will remain the main driving forces behind 5G. So for 5G requirements, we are talking about a peak data rate about at least 10 gig. Sometimes it can reach 20 gig for the downlink. And for the user experienced data rate, we are talking about a minimum of 100 megabit per second. For the massive machine type communication, it is expected that about 1 million devices per square kilometer will be connected. And the most important use case is also the ultra reliable low latency communication, which is very important for critical mission applications like remote surgery or intelligent transportation systems, where the requirements for this use case is to have a latency of less than 1 millisecond, which is really challenging. So in this slide, I'm just comparing the improvements done from 4G to 5G. As we can see here, for spectrum efficiency, we're expecting an improvement 3 times. For the mobility, we are expecting like a speed of 500 kilometers per hour. This is for high-speed train, for example. And there is also the energy efficiency that will go beyond the 10 times improvement. In this slide, it's presenting the actual the level of importance of these use cases. For example, for the enhanced mobile broadband, mobility, spectrum efficiency, user experience, data rate, and so on, they all have high importance. However, if we, for example, take user experienced data rate and mobility, they cannot have that level of importance at the same time. For example, if we are in a hotspot, we can trade high data rate for mobility, for example. Anyways, this is just to review these key capabilities of 5G. These key capabilities can be achieved by these 3 prominent technologies: mmWave, massive MIMO, and HetNets. So this is a nice combo. They work nice together, and each of these requirements is compensating for the other. So mmWave, why? Because of the huge bandwidth that is available at these frequencies. And mmWave works very well with massive MIMO. Okay, because at these frequencies, we can afford to pack a great number of elements, and we can compensate for the high path loss that mmWaves is facing. Massive MIMO, we're talking about hundreds of elements to serve about 10 users. So this is just following the traditional MIMO that is used for 4G. 4G, we're talking about 8 elements at the base stations, 2 to 4 at the mobile station. Here we're talking about hundreds. Sometimes 60 elements or 64 is also considered as massive MIMO. What is the benefit of massive MIMO? First one is spectral efficiency. This is known by MIMO. And this is mainly due to the fact that we are using aggressive spatial multiplexing. So by using this 100 elements, we should be able to distinguish between users, and we can use it as multiple access techniques, actually. Energy efficiency, because we are using massive MIMO, we can focus that energy with really sharp beam, and because of that, we should be able to reduce the transmitted power per antenna by an order of the number of antennas. If we're using 100 antennas, we can reduce that power by 100. Another benefit of massive MIMO is because of this number of antenna, we can face rich scattering, especially in below 6 gig. I will talk about waves that does not fit within this category here, but with massive MIMO, we can have that rich scattering, or what we call also favorable propagation channel. Means that you have orthogonal channels, and each user actually will be having its own channel that is orthogonal to the other, and we can use those old techniques that were used by CDMA and so on, because they can be seen as special signature from each user just by the channel itself. Another very important benefit of massive MIMO is they rely on the law of large numbers. Many studies on MIMO, they will also, when it comes to deriving, for example, the closed form of the probability of error or the system capacity, we do some approximation. We assume we have a large number of users, we have a large number of antenna, and we come with the suboptimal solution. Now that we can use massive MIMO, we can be close to those optimal solutions, if not with just simple detection techniques like maximum ratio combining or maximum ratio transmission if we are dealing with beamforming or detection. So this is one very important parameter. As I said, the two last points are more targeting the below 6 gig performance. For waves, as I will talk, as mentioned later, they have limited scatters, and there is a special model for these channel. This is one example of the test bed for massive MIMO. This is an example for below 6 gig using 128 elements, and each element is connected to this white platform that you see at the bottom. These are US RP software defined radio. We have a couple of these at RMC. Each platform actually can do 2x2 MIMO, and you can combine them together to scale up your system. And you can see the amount of cables that you need for each chain. Okay, this is the actual traditional way how to do beamforming. So you need to have, from each antenna, you need to have, it should be connected to your RF chain that has the analog to digital converters, and you have also the beamforming weight that adjusts the gain and the phase at the same time. And this becomes expensive, of course, especially if we are targeting high performance ADC or digital to analog converter. HetNet is another prominent enabler for 5G. It started with 4G, of course, but here when we use small cells, we can have a small coverage, we can have high capacity, and we can have less interference. And this works very well with the waves also. Waves, short range application with massive MIMO. So that's why whenever we talk about wave, we talk about massive MIMO, and we talk about HetNets. Of course, in HetNets, they can be used at the access level, the access link between the mobile users and the antenna if we are using small cells, for example. So we can have waves or massive MIMO between the mobile users and the base station. And we can have it also at the backhaul link between the base station, the small base station, and the macro base station. And for this scenario, we published a paper on how to improve the capacity of the uplink using massive MIMO and using a capacity-aware algorithm. Some limitation, for example, we have the channel estimation problem due to pilot contamination because we have a limited number of pilots. And when the mobile user sends their pilot to the base station, they might interfere with each other, especially if we are reusing the same pilot. The TDD mode also, this is the mode used versus the FDD mode. Because with the FDD mode, the overhead is dependent on the number of elements that we can use, especially with massive MIMO. This becomes very big, and it's not very practical. That's why massive MIMO is restricted to TDD mode. It has a benefit, of course, whenever we estimate the uplink channel, we use the reciprocity to downlink the data because we can use the same channel for the downlink. The last challenge is the number of RF chains. As I said, imagine that you have 100 elements, and for each element we need, especially the analog to digital converters, which are very expensive if we are talking about high performance digital to analog converter. For this one, I will talk about the solution that is very attractive to solve this problem. And I will skip the first one because of the time. Okay, so this one's just about pilot contamination. This is just to compare the overhead of the TDD mode and the FDD mode. As you say here, for the FDD mode, the overhead is, if we are talking about key users in the system and a base station that is using M antennas, K plus M should be less than the coherence time. Coherence time is the time within which your channel is assumed to be stationary. So coming back to the last challenge of having this number of required ADC and DAC. So the same problem in terms of cost and power will happen if we'd like to go fully analog. We can have RF gain, but these are also very expensive. So the solution is to partition the beamforming between analog and digital. Okay, so you can still have our massive antenna at the analog side, but that analog beamformer will rely only on the phase shifters. Okay, so we constrain our analog beamformer just to steering without any gain control. And the shortcoming of that gain control we can compensate for by using the digital beamformer. So we combine analog beamforming with digital beamforming by using less than the number of antennas at the RF chain. So this is an example of going, let's say, from 100 elements to 4 RF chain. This is a huge saving in terms of cost and energy. There are actually 2 architectures that can be used for this hybrid beamforming, and this is very attractive. And the picture I showed you before about that test bed with those bulky cables, we can imagine that we can reduce those cables to 4 cables, at least the one that goes to those software-defined radio. Instead of using 60 defined radio, they are very expensive, about 20,000 each. We can go with a few software-defined radio. So there are two categories here, 2 architecture. There is a full connected structure where you have your RF chains, I mean the one that goes to the digital beamformer. They are all connected. Each one of these are connected to all the phase shifters that are present at the RF level. The other one, the first solution, actually, the fully connected will give you, of course, an optimal performance. The other one, it's you divide your massive antenna into sub-array, and each sub-array actually you use phase shifters. Here you can use NT divided by RF. See, if we assume that you have NT elements and you have n RF chain, so n RF chain is less than NT. The example I give you, 104, and you can actually use only NT divided by N4 phase shifters. Of course, the performance of the second structure is suboptimal, but it is less complex than the first one. Another, okay, maybe I will just talk about it later. So this is another challenge is in terms of processing here. This is an example of just a single user, just to show you the picture of the complexity that we can have here. So we have digital beamformer, the analog beamformer at the transmitter side, that is transmitting the signal by using this combined beamforming. At the receiver side, we again multiply by another combined beamforming. That gives you an idea about the signal, the expression of the signal in terms of these two beamformers. The joint design, or the joint, to try to optimize these two weight vectors at the same time is challenging, okay? And the problem becomes non-convex, non-linear, and name it. It's not very practical. Another approach that is more practical is to somehow you need to determine, you need to do it in two stages. For example, you need to determine your analog beamformer. Once this analog beamformer is fixed, then you can try to optimize your digital beamformer, and you can use, in this case, you can assume that you have an effective channel, which is your H times the AT, the analog beamformer that you have calculated at the first stage. So basically, once your analog beamformer are done, you can just do the regular approach by optimizing your digital beamformer. For waves, as I said, we have limited scattering, and we have more coherent channel than the case of rich scattering with below 6 gig. So that's why one well-known model that is used is what we call the clustered channel models for waves, where we group all the scatters that comes from similar direction of arrival or similar delays. We combine them in one cluster, and we have this expression of the channel model when you have your the array response of your mobile station and of your base station. I didn't show the other side, but this is just one side uplink or downlink. And we have the angle of departure and the angle of arrivals. The angle of departure here, we are assuming just the average angle of arrival, but you can go more precisely, but assuming really all the angle of arrival from the scatters that are belonging to one cluster. By using this model to capture this wave behavior, so if we go, for example, with the optimal analog beamforming, let's say we have an optimal analog beamformer or fully digital beamformer. For this example, we have 64 by 64, so 6 clusters. We have assumed 6 clusters, and within each cluster we have 8 scatters, and we have an angle spread of 5 degrees. For this optimal solution, we have assumed the singular value decomposition, or what we call also eigen beamforming, when you just do the eigen decomposition of your channel. Okay, so if we assume that we know the channel in this case, and we do our eigen decomposition, we end up with this response of the pattern. So the beam pattern will look like this, and even with this number of reflection and scattering, because of that model, you can see that we have a limited number of dominant beams. Okay, we have a limited number of dominant beams. This is for the unconstrained case, means that we are assuming that we are adjusting both the phase and the gain. Of course, if we and this, of course, will match the optimal solution. If we constrain our analog beamformer, let's say we cannot adjust the gain, okay, just steering the beam, of course the performance would be less. But by combining by compensating for that shortcoming of the analog constrained beamformer with the digital beamformer, the low picture showed you basically the same pattern, especially for those dominant beams, which means that with combined beamforming, this is, by the way, we are using 64 by 64 and using only four RF chain at the digital beamformer. So with 4 RF chain, we were able to reach the performance of an optimal performance of an optimal beamformer, which is a huge improvement. Another way to do it, which is very attracting too, is using Butler matrix. Most of you know Butler matrix. Basically, it does integrate some phase shifters, and you can just scan the ports of this Butler matrix, and for each port you will end up with a different beam position. So the first thing you can do, you can search the port that has the maximum power, and you can select those beams. You can select the best beams. Let's say you are targeting to use 4 RF channels. So you can work with the best 4 beams, and these are the channels that you will be using to improve your digital beamformer. Of course, scanning all the 64 beams might be a little bit too much. So there are ways how to avoid that. Some studies have suggested to use subarrays and using Butler matrix just in each subarray. In this way, you don't have to scan all the 64 beams. Or you can use this into stages, like using a code book where you store a number of weighting vectors that will achieve beam pattern with different beam width. And from this, you can start with Y beams, for example. You can start with Y beams just to have a rough idea about where your target is. And once you are done, once you are done with this first scan, then you can move to let's say 16 by 16 Butler matrix, for example, to have a narrower beams. Once you are closer to that target again, you can go with 64. So this way you don't have to scan all the 64 channels, but you can do it just for the area that is the area of concern. And this way you can have your for example, here we end up with 4 beams using 64 by 64, and once you combine it with your digital beamformer, then you get your actually beam toward that target, which is the optimal solution. So these are just some contribution. As I mentioned before, this is for using massive MIMO for both access links and backhaul links. And we have shown here that using this algorithm that we have proposed, capacity aware, we can improve the system with respect to the macro cell system. We have also applied massive MIMO to wireless sensor network when we have different clusters, just to mimic the antenna array. So these sensors, they can cooperate to form a massive MIMO, and they can actually be used to improve the transmission toward the base station. So we have just extended our algorithm to wireless sensor network by using this clustering method. And this afternoon I will present this paper, so you will have already an overview of the hybrid beamforming, this paper about a hybrid beamforming and using capacity aware at the digital level and eigen beamforming at the analog level. I will then go quickly for that paper this afternoon. Another interest that we are looking for is the MIMO radar. We can extend actually these performance to MIMO radar. One of the benefits of MIMO radar, for example, is the resolution that you can obtain from this MIMO. If we use, for example, here 1, 2, 3, 4, 5, 6, 7, 8 elements, we can get the resolution of 15 elements. Okay, 8 times 5. This is, we create a virtual array, and we can actually benefit from that virtual error, like if we are using 15 elements phased array. And there is a room to apply also hybrid beamforming into that example. This is just one research that was done with one of our master students here, using instead of using software-defined radio, we have used here a network analyzer, and to detect like 3 targets here. You can see here from this experience that with this MIMO system we can actually improve this system. You can see here we have 4 ports. So imagine if we use like a massive MIMO at the transmitter side, at the RF chain, and we can still afford to use those 4 ports for this network analyzer. Of course, with software-defined radio, you have more flexibility in terms of generating the waveforms, but this was a first test with the network analyzer, as we were facing some problem with the actual USRP software-defined radio. We had some problem with the coherency. The daughter board cards, if they are not well selected, sometimes they cannot allow you that coherent processing, and that's why we faced this problem, and we solved it by just using this software-defined radio. And that's it. That's it about the presentation.